Afternoon, everyone. Welcome to this month's webinar hosted by the Data Science Across Disciplines Research Group. Today's speaker is Dario Fanucchi, who's the co-founder and CTO of Isazi, a data science and machine learning company based in Joburg, South Africa. And he'll be speaking to us about hierarchical forecasting for demand in supply chains. Thanks for being here, Dario. We look forward to it.
Great to be here, Cherise. Thanks for having me. Okay, awesome. So I'll get kicked right off. Can I start by just talking a little bit about our approach to data science and some of the problems that I've solved in the last 10 years at Isazi. And then I will sort of narrow the focus down into specifically hierarchical forecasting, why it's important, and what we're doing in this space. I guess a disclaimer up front is it's all pretty much linear algebra, so it's nothing too fancy. All right, great. So let's start by just looking at some assorted examples of problems. And I guess just as if people in the audience are either aspiring data scientists or are just starting in this field, it could be interesting to get a flavor for the kinds of things that you have to sort of come across and the kinds of questions that you ask. Essentially, I like to view data science like, you've got this world you can interact with, kind of like real science, right? And you can ask questions and you can probe and you can try to find patterns and try to solve problems. And effectively, that's what it comes down to. So I've picked three. In the last 10 years, we've done 130 odd. But here are three that I thought, just at random, could be interesting just to touch on quick. The first is kind of, you're given a cell phone, and you can imagine this would be like an insurance company that would require this. You're given an app on a user's cell phone, and you want to be able to tell if they've had an accident so you can alert emergency services, or if they're like doing naughty things like calling people on the phone while they're in the car. And so just using accelerometer data and gyroscope data, how well can you do at this problem? And I guess I'm just gonna phrase the questions here. There's a whole world of experimentation that you need to do to answer them. But I just want to give a flavor for the questions in this piece. And if anyone's interested, you're welcome to ask me later. Here's another one, which is, typically a radiologist in the morning will have a big pile of a stack of documents on their table that they have to go through, and maybe 5% of them are urgent, but they don't know which 5%. So can you sort that stack to put the urgent ones on top so that they get seen to first, right? I mean, so you're not asking the question, can we replace the human here? Because that's very difficult in medical industry, and with the brittleness of machine learning, which is a whole other discussion. But can you at least, on balance, make the important stuff come out first, so that it gets dealt with whilst the mind is fresh, and in advance you might help to save lives. And again, that's a question, and then the answer is a whole other thing, right? Collecting data, experimenting with it, seeing if you can even make head or tails of it outside of a test set, and so on. And the last one is, you see the picture here is just Cape Town, actually. And what you see is every farm or house or property in Cape Town mapped by its price and its size. The size of the box is its size, and the color is a price. And obviously you can see patterns immediately in sort of the Western Cape, the peninsula there. But the interesting question here is, can you predict the selling price of every property? What is the next selling price going to be? Or if it were to sell now, how much would it sell for, right? And you can understand that a lot of people are interested in this problem, one of which is the tax man, right? And again, there's lots of interesting ways to solve this, some of which would be like to use Gaussian processes, for spatial modeling, but yeah, just leaving the question open. And here are some more questions since I'm at it, but these ones are a bit more like just to try and get people thinking. How would you go about? You're at a movie studio. The cost to dub a movie is too expensive. How do you dub that same movie in 1/100th of the cost? how do you deliver data-driven education to students who have no internet and no tablets? How do you diagnose 400 million children when you only have 15 radiologists? And that last one, I guess, overlaps a bit. So the product I'm going to be talking about today is the last one. But we do have 4 that are quite interesting, and they all have really interesting problems that come out of them. And they all arise from questions like the ones above. So again, just reinforcing this notion that everything starts with a big question. So the first one is we wanted to decrease the cost of in-store analytics by a factor of 100 using something. The second one is we wanted to orchestrate millions of tasks without any managers. We're currently doing about 1 million per day. The third is, can you make sense of unstructured documents? That's very broad. And the last one is the one we're really going to zoom in on now, which is kind of, we have this ambitious goal of reducing the cost of living by making all the supply chains more efficient. And what are the steps you'll take along the way to achieving that? So just here's some of the things you do with shelf analytics, detect the products, tell me what the price tags say, tell me where the shelves are, but there's, a lot more depth to it than that. Here's some of the things you might do with crowdsourcing. You've got like an algorithm crowd and a human crowd, and you play them off each other, and you can do clever things to kind of find consensus, do feedback loops, train algorithms, and so on. And what are the questions in document intelligence? But I'm going to just go straight to kind of the Hudson Platform, which is sort of the origin of today's talk. And this is the only salesy slide that I've got in this talk. It came out of a sales pitch, so please excuse the non there's no equations on this one. But the idea behind the platform really is that we just pulling in data from all over a business. It can be messy. The reality of the space is that it is messy. It comes in emails, in spreadsheets. Some of it is coming via SFTP. And the first thing we need to solve before we can even begin to start actually asking mathematical questions of this data is just tidying it up, orchestrating it, and basically getting it into a single place where it can be properly used. And that is sort of probably the most difficult part of what any data scientist ends up doing, is building these pipelines, hundreds of pipelines that are bringing data in and trying to make sure that the data is of sufficient quality that if you do machine learning on it, you will actually get results and not just noise. And on the other side, there's things that we're focusing on. Remember, our aim was to make supply chains more efficient, sort of in many supply chains as we can, so that we can really drive down the market forces that will drive down the cost of living. And we started with some big multinationals, and the thing that everybody needs is a demand forecast that doesn't suck. And that's actually quite difficult to do for reasons that will become apparent shortly. We optimize inventory planning. That's a nice sort of mathematical optimization problem where you're kind of solving for the minimum risk. You've got like a portfolio, which is how much stock do you put in your warehouse of every product that you're selling? And you're trying to minimize your risk or maximize your expected future reward. Effectively, I want to be able to sell, but I can't sell it if I don't have it. But if I have too much, I'm wasting money. And so there's this optimization problem that comes out of that. And there's even a deeper optimization problem, which is your sort of facility location and logistics problems that are related to now, how do you move stock in a network? And all of these things are really interesting, but none of them would work at all if you don't have a good forecast. And so it's sort of the bedrock of all of this is you need a forecast, and it's kind of important at multiple scales. If in a supply chain, if I don't know how many I'm going to sell of these, what's this, earbuds or whatever they are, if I don't know how many I'm going to sell of this, I can't plan to keep a certain number in stock. If I don't know the volatility of my sales, I don't know how much of a safety net I need to keep, or I might keep too much, or I might not have enough. And this is happening all the time. I mean, there's been in the news quite a lot. The Suez Canal got blocked and a whole bunch of companies lost billions. There was a delay in shipping due to issues in China with steel. And you know, again, people weren't able to get their products. So getting a forecast that can at least understand the uncertainty in your demand and try to model it as close as possible is super important. And it's important at different phases. In the long term, it's important for sort of business and budgeting. But in the medium and short term, it's important for the actual optimization that you want to do of the supply chain. So I'm going to go all the way to hierarchical forecasting. But before I do that, I guess, you know, the first thing that we should look at is just general time series forecasting. So we're going to do a lightning tour. I'm not going to be able to go to any of these in any kind of depth. But, you know, how do you predict time series? You know, I've got the amount of sales of this thing for the last year, every day, for the last 3 years. What do I do with that? So there's a couple of different approaches that people take to this problem. The first is time series regression, which is actually underappreciated. Most people jump straight to the sort of more traditional time series models like ETS or ARIMA. But you can do a lot with time series regression, especially if it's a business time series. And that's effectively where you just take like the days of the year and you create Fourier components out of those days of the year. And you might add other features like whether it's Easter week or not. And that moves around from year to year, right? And you've got all these features that are essentially functions of time. And then you regress your time series as a function of those features, which are functions of time. And so you end up with a function of time. And you can just fit any old regression. It could be linear or non-linear. And this can be very powerful. And in fact, a lot of the new methods are extensions of this to some extent. But there's traditional approaches that people do take. So ETS is kind of like an exponential smoothing approach, but it's cleverer than just, you know, smoothing. You also look for trends and seasonality, but you fit them in such a way that you're basically taking a weighted average of two prior points at all times. And that's why it becomes sort of an exponential smoothing. And it's quite heavily used when there's a trend. ARIMA, that's your sort of integrated moving average, your autoregressive integrated moving average, is all about getting rid of what's sort of your autoregression in a time series. So often nearby points in a time series are correlated, right? So they correlate to each other. Your autocorrelation is your correlation to yourself as a time series. And that thing is pretty much, you know, if you plot it, you can see that points that lags 1, 2, and 3 from each other are often quite correlated, you know. So you can take the series, you shift it, and you take the correlation of the series with the shifted copy of itself. And you find that these two things are often quite correlated at various lags, right? And so ARIMA is all about removing that correlation. You know, you do this by differencing and regressing. It only works when it's stationary. But where I find ARIMA to be very useful is actually whatever fancy forecasting method you have, you take the residuals of that to your actuals and you run ARIMA on that and you add that as a term at the end of your model. And that can basically take care of any autoregressive error or autocorrelation that might occur in your error, which basically will give you a better result. LSTM is a neural net model. It's very good for like something that's physical, like, for example, gas pressure. It's very bad for business series. I've actually never seen an application on a business series where an LSTM has worked. That's generally because it needs a high data resolution, and business series are typically sort of daily or weekly, which doesn't give you very much data to fit a very highly parameterized neural network on. Unless you apply some tricks like batching certain series together and trying to embed their parameters into a latent space. Then there's 2 recent papers that were sort of launching new methods. Profit was released by Facebook in 2017. They're using something called a generalized additive model, which is basically like a time series regression, but Bayesian. And you know, you can add your dependent terms and try to learn things like change points and so on. And then Gray Kite was released by LinkedIn more recently in about 2021. And it basically is time series regression, but it's got change point detection and some other clever tricks. So please do check out these papers. And there's obviously open source code that goes with them that's quite useful. There's another reference here, which is Hyman's forecasting book, which I think is a very good reference for anyone opening or starting out in this field. But I think, you know, the general thing is there's quite a few methods out there if you want to forecast a single time series. Here's an example of time series regression, where effectively you're seeing kind of a whole bunch of different factors that are functions of time being baked into a forecast. And the blue line is now the forecast. You can see that it can see a Black Friday coming, a start of year dip, and so on. And these things are effectively, you know, what you would expect out of a time series regression type model. There are some sort of things to note when you're doing forecasting of business series, especially supply chains, which are notoriously difficult. There are lots of things that are quite outliers, but definitely kind of, you know, exceptions that need to be dealt with explicitly. If you don't deal with them explicitly, they bias your model. And so I've got lockdowns and looting as an example here. This is the sales, I think, of one of the largest retailers in South Africa. A lot of their stores were burnt down in the looting week. And you can basically see here that in that week, the sales obviously went down to zero, right? And if you try and predict using this data without doing something, you know, like adding a regressor that tells you about this or removing this data point, you're going to obviously bias your model. You've also got sort of Black Friday. You can see that there's a big, in South Africa in particular, in retail, massive impact of promotions on sales, which often confuses our international colleagues who come along and try to do data science on South African data. And then you've got things like panic buying because of lockdown, which was a super irregular event, but it causes these spikes in the forecast. So, you know, as soon as you're trying to predict things, you've got all these issues that need to be taken care of first. So I think, you know, and there's also a very interesting thing that is unique to supply chains, which is that typically the demand is quite fluid in time as well as in, you know, customers. So if I go to one shop looking for these earbuds, for example, and I can't find them, I'll probably go to another shop, which means the demand is fluid in space. If I miss one store, I may go to the store next door and try and buy them there. The second thing is the demand is fluid in time, because if the store is out of stock today and gets stock tomorrow, most likely that same person will come back tomorrow and buy. And that is very unusual. You know, it's not true of like a physical time series like gas pressure. And a lot of the methods like ARIMA or ETS get completely thrown out by this component of sort of supply chain time series. And it's one of the main motivators for what we're going to discuss next, which is this sort of hierarchical combination. But it's a very tricky one because, you know, you have to combine things at different time scales in order to get the right answer. Here's a more complex example of a forecast. This is kind of a forecast that starts at the consumer and ends at how the retailer will purchase from a supplier. And it actually models that retailer as an agent. So you've got kind of an agent-based model that is running in order to try and parameterize how that agent is making decisions and assuming that they make optimal decisions. So we'll assume that ShopRite or Macro are going to make optimal decisions about what to buy in order to keep their stock down, in order to maximize their sales, based on their understanding of, you know, demand. And this, then you feed this into an agent-based model, which you can fit. You can fit the parameters of the agent-based model, and effectively that enables you to create a new forecast, and that forecast can have more meaning. It can be interpreted better, but also often is more accurate in the sort of general scheme of things. So this is an example of a very complex system that you might set up. And the idea is that each one of your individual forecasts may be complex. It may have its own characteristics with regards to bias and error. Obviously, it will model its own bias and error if you do it properly. But you know, they may not all be just ETSs or ARIMAs or whatever. And it shouldn't matter. So I think I took nearly half an hour to get to the meat of the talk, but here we are. So I can slow down a little now from our lightning tour. I want to discuss a kind of not so well-known technique, but it turns out, but also have in the back of your mind when you're working with business time theories in particular. So here's a bit of a motivation. When you're dealing with, for example, the sales of every product in the country at every store in the country, let's say that's your data set. It's a data set that we've been working with. It's a massive data set, right? You've got thousands of stores, you've got thousands of products. For the sake of this presentation, let's just use round numbers, 1,000 products in 1,000 stores. It's actually kind of an order of magnitude bigger than that. But let's go with 1,000 products in 1,000 stores, and you need to predict this 700 days into the future. So you need to make just about 1 billion forecasts every time you make predictions, right? It's 1 billion predictions that you're going to have to make. And that's a lot of predictions. So, you know, you could make them one forecast at a time, and that will take time. It takes a whole day to effectively make one prediction at a time. But the problem with that is you miss a lot of that structure, like what I was talking about, when if I go to one store and I can't find it, I'm going to go to the next door store and buy it. There's this idea that the amount that you sell in a region, for example, in Gauteng, will be much more stable and much easier to predict than the amount that you will sell in, I don't know, Ganonsfontein, or I don't know, Crocodile, or wherever random store that you so happen to be looking at in your data. That's very noisy. And in general, the stores that you will see just sort of from the data are very different. Like here's 3 on the top here. The red and the green one are kind of correlated. You know, they tend to spike at the same time, and that's related to payday and all those things. Although there are some strange behaviors in the green that aren't in the red, and there's this weird sort of offset spike here. And then the blue one is like completely different, much smaller, much more volatile. And these are 3 out of a couple thousand. And so when you try and plot them all, you get the smudge, right? But the smudge has some interesting regularities. And those regularities are much harder to detect in the individual stores, especially in the smaller ones. And what I haven't mentioned is that when plotting these time series for the stores, I just added up the value of all the products that I had in my data set. And so, in fact, it's already been regularized by adding up every product up a product hierarchy to the top. So when you're dealing with a super noisy bottom of the hierarchy, like a product at a store, and you try and make a prediction, your prediction is basically just going to look like error bars, a whole bunch of error bars and basically no signal. And so, you know, how do you combine all this information from the top of the hierarchy to the bottom of the hierarchy in order to get better predictions, you know, all around? And that's kind of the question that we're trying to answer. Here's another example, and it's kind of another motivating factor for why you want to do hierarchical forecasting and not, for example, try something with multivariate time series, which is very much a kind of an alternative approach, but even also a compatible approach with this. So a very compelling example is in the case of a supplier, you know, like someone who makes these products. In the case of a supplier, they have monthly or quarterly targets that they need to hit in terms of sales, typically. And those targets are not meaningless. They're actually super predictive as feature variables because the entire company is chasing it, right? So, you know, you're creating an effect. That target creates promotional activity. It creates all kinds of activity in the business that then drives the sales. It is often visible to the people in the factories who make sure that they produce enough in order to sell that much. So pretty much those targets are attractors. They're something that gives you a good signal on the forecast. But the target is written in rands, and it's often not for a single product. It's often for a whole group of products over the whole country, or maybe for a single group of customers. So it's not compatible with kind of, you know, it's not a product at a store. That target is not written at the level of a product at a store. So you have to aggregate or add up your forecasts to even see something that is relevant. And in this case, you may even have to change your units from how many of these will I sell to how many of these and how many of these will I sell. This is what I had lying around. Do not ask why. How many of each of these different objects are selling, and maybe I'm going to aggregate them all up and work them out into rands, and that's the number that I'm going to try and hit, and that's going to be a very predictive number. And so I'd like to take advantage of that in my prediction. The other thing is that a retailer does the same thing. So for example, ShopRite Group will set targets for how much ShopRite, Checkers, Usave, and all of these different brands are going to sell. And if you look at like this map, you can see that I just plotted where all the stores are for Checkers, Usave, and ShopRite. They've got a whole bunch of others in their portfolio, but I don't want to make the graph too messy. And you can see just from the distribution of the stores that they have different purposes. The green is Checkers, and you can see it's basically at the business hubs, right? There's almost very few of these in sort of rural South Africa. And so you can already tell that they're going to have a completely different strategy in how they sell and what they sell to, for example, a Usave, the red one, which you can see all over. It's much more well distributed. They have lower prices. I mean, a lot of things about their data is very different. Some of the stores are actually trucks that just, you know, rock up and sell out of the truck. So you've got such different things that aggregating up to just all the Checkers or all the Usave or all the ShopRite makes a lot of sense. And you want to be able to use that information because these things drive the behavior of the people that make the decisions that govern the demand that you're trying to predict. So my last piece of motivation, in case I haven't convinced you yet, for all you sticklers out there, is kind of, okay, we've talked about why you might want to aggregate up to Checkers or aggregate up to ShopRite, you know, because of their strategies, or aggregate up to all devices similar to this one, right? In a product group, or washing powder, for example. But we haven't talked about time, and time is also important. So, you know, another kind of, another interesting thing is that you can aggregate week, month, year, and those are also kind of, you know, like I said earlier, if I don't get it today, I'll go buy it tomorrow. And so there's also sort of a lot of flux, at least in supply chain, in these dimensions, right? So here's kind of an example of a store hierarchy. You've got your 1,241 stores, that's how many ShopRite stores there are, broken up into region and store formats, broken up into the 11 store formats, of which 3 are ShopRite, Checkers, and Usave, and then you can take that all the way up to the top. And every single one of these nodes has got a time series, and you can predict that time series. And if you think about it, you know, I might predict these with different methods, but if I try and add up the predictions I make at the bottom and see how they stack, they're not going to quite line up with predictions I make at the top. And that's what you're seeing here in this graph. This one, I think, is the breakdown of, I think it's Massmart data, but in any case, it's basically sales of one of our customers' products. And you can see that the black line, which is the prediction at the top of the hierarchy, doesn't quite line up with the sum of all the colors, right? Which means that even if I'm predicting at a customer group level to begin with, I don't get perfect sort of, it doesn't line up. But now, which one do I trust, right? Because they're all done with forecasting methods. They've presumably all got you know, some logic behind them, and they might even publish their own errors, right? But let's assume that they all have a similar error distribution for the moment. How do you know which one to trust? And the answer is, surely, if they're giving different answers, somewhere in the middle is the safest guess. It's sort of the law of averages of experts, right? Which is proven again and again to work quite well. So there's all the motivation for why hierarchical even makes sense, especially in supply chain. I'm going to do a simple example to kind of start to address the question, how do you even do this? And it's going to be very simple, so my apologies to anyone who I bore with this, but here's an example where I'm just taking a single time step. Remember, at every node, I've got a whole time series of predictions. I'm just going to take the first time step of that time series, right? And I'm just taking a very simple hierarchy where there's basically three, you can think of it as three stores being added up into a final result. And my prediction at store 1 for time 1 is 10, at store 2 is 20, at store 3 is 25. But when I predict for the whole country, I predict that I'm going to sell 45 units in time 1. And when you add up 10, 20, and 25, you get 55, not 45. So these are incompatible forecasts. So we would like to make them compatible, but we'd like to do so in a way that is sort of principled. So the structure is not consistent, as you can see. They don't add up. So what if we replace the top prediction with 55, right? Because the bottom predictions all come out as 10, 20, and 25. If we replace the top prediction with 55, you know, that's a consistent structure now. So we throw out the 45. That's called a bottom-up forecast. And it's extremely popular in supply chains. If you speak to any supply chain that's doing forecasting, you'll find that most of them do this. And one way to get a handle on how accurate this is to just see how close it is to all the different forecasts we made, added up as a sum of squares of errors, right? So all I'm saying is each of my point forecasts that I made at t equals 1 had some reason behind it. And so presumably there's a Gaussian centered there with some width, and I'm going to assume that width is just 1 everywhere, standard deviation of 1. So let's add up the sum of the squares of the errors to those original forecasts and see what happens. So because I replaced the 45 with 55, I incur 10 points. I'm far away by a factor of 10 there. But at the bottom, I'm exactly spot on what I said. So I'm not deviating at all at the bottom of the hierarchy. So these are all 0. And my total squared error is 100. And so the question is, you know, if squared error is the measure by which I want to sort of measure this, and it's not a terrible measure. It's you know, a distance in some space to an Euclidean space to the forecasts that I made at every node of the hierarchy. Can I do better than bottom up? And how much better? So intuitively, and you can if you want to prove my intuition, you can just think about Lagrange multipliers, or there's a lot of ways to prove it. Actually, you can just take a gradient. But intuitively, I should try to make all these errors equal, right? Because if I spread the error equally, then the squares will be small. I'll be summing up small things. So let's just do that. What I did now is I took, how much must I take? 2.5 basically units, because I've got a total of 10 that's different, right? So let me divide it into 2.5 in the top, 2.5 there, there, and there. So that'll add up to 10. And so basically I turn the 10 into a 7.5, the 20 into a 17.5, the 25 into a 22.5, the 45 into a 47.5. And you can check that the green numbers do in fact add up to each other. They're consistent with each other. So this new green forecast is consistent across the hierarchy at t equals 1. So it's consistent by design. We spread these 2.5s. But what's the error look like, right? Intuitively, we know it's minimized, and you can prove this quite easily with differentiation, but let's just check what it looks like. So, let's work it out. It's basically 2.5 squared in each position, right? By design again. So that's 4 times 2.5 squared, which apparently is 25. Yeah, I think that is correct. Yeah. And 25 is 1/4 of 100. So you kind of, when you take square roots, you're kind of half of the error. So that's, not bad. That's quite a big reduction in distance from forecasts that I spent time and effort to produce in the first place. and that may have had real reasons for why they're there, based on business logic. So this gives me a closer forecast to all of them that is consistent and that adds up across the hierarchy. And I would replace then my bottom nodes with these green ones. Now, this can be extended quite easily to a much more general use case. So I'll just quickly go through that. It turns out that, it's actually quite easy to do this. There's just the constraints that we've given for this hierarchy are just linear, right? So let's just understand what I mean. Let's call these bottom green items x tilde 1, x tilde 2, and x tilde 3, right? They're my new forecast, they're x tilde. And the rest of the hierarchy will just be governed by adding these up, right? So I don't need to give a name to this top guy. If these are the x tilde 1, x tilde 2, and x tilde 3, the only constraint that I have is that the top one must be the sum of the first 3. And so that's just this row of the matrix here, which is basically that y, your top node, must be x tilde 1 plus x tilde 2 plus x tilde 3. And then x1 is just x tilde 1, x2 is x tilde 2, and x3 is x tilde 3, which is kind of obvious. And then obviously this is not perfect. There's an error involved. And that's the sort of error vector that you incur. And now the whole problem when you phrase it like this basically comes down to solve this system of equations whilst minimizing the sum of squared errors, right? So minimize the norm, the Euclidean norm of this vector over here, the errors that you end up with, right? And this is sort of a well-known problem, and just in complete generality now, I don't care about this particular hierarchy anymore. For any hierarchy, I can phrase it as a structure matrix like this, S, which I multiplied by my x tilde, and I get an error vector. And now I want to find x tilde in such a way that my error vector is as small as possible given S and X. So we call this matrix S of 1s and 0s a structure matrix. It's got 1s and 0s because it's basically inclusion, exclusion. Every row is a constraint in the hierarchy, and you're either including something in the constraint or you're not including something in the constraint. So you can express pretty much any hierarchy in this way. You can imagine that every node, its children, you can just follow them all the way down to the root, and that is the things that you switch on. That is the things that you switch on in its row. So that's what makes up that node in the hierarchy, right? And geometrically, it's actually quite sort of simple what we're trying to do here by trying to minimize this error vector. S describes a kind of a column space, right? Which is like a hyperplane. And we're basically saying, find a point in that hyperplane, that's what this is, and then take a vector from that point to your answer. And it's clear that it's going to be a normal vector, right? Otherwise it's not minimized, you can always find a shorter one. And so you're basically trying to project this point into this column space, and that's all that it turns out to be. And so, the formula for that, you can use the more Penrose pseudo inverse. In reality, you'll use a numerical solution. You won't actually compute the inverse, but it's got a closed form formula at least, even though you won't actually use that, and that's it. So just to give you an example of how you might construct the structure matrix in a kind of slightly more real worldish problem. I've got 3 products: the circle, the square, and the triangle in Shape Factory. And Shape Factory is selling to 4 different shops. And basically, it sells squares, circles, and triangles to each shop, right? But at each shop, I've also computed a forecast of that total shop's sales, right? How much that shop sell of squares, circles, and triangles combined. And then I've gone even further and I've bunched the shops into sort of shop types, which I've named for no apparent reason. In Flatland, there's also a ShopRite and a Checkers. They're very pervasive. And the Flatland ShopRite and the Flatland Checkers sell squares, circles, and triangles. And they have budgets and targets that they keep, which they've been basically computing forecasts for, and that's what's being kept in a time series at these nodes. And finally, you know, the GM of Shoprite/Checkers Flatland is also interested in the total sort of numbers that he sees in his market report. But in addition to that, the square, circle, and triangle factory also have targets for the total number of circles that they sell, the total number of squares that they sell, and the total number of triangles that they sell. And they track that by adding up the circles across all of the sort of stores that they sold, and adding up the squares and adding up the triangles. And that's what these black, blue, and red lines are all about. So this is kind of a hierarchy structure. You can imagine it's a much simpler one than what you deal with in reality, but it is similar in nature. It's not a tree. It's not a tree because this sort of circle belongs to two parents. But it is a directed acyclic graph, and that's what matters for constructing a structure matrix. So let's construct the structure matrix. The first thing you do is, let's get out of the way the fact that the structure matrix is going to have a copy of I12 in it, right? And I put that down the bottom here, which is basically just saying the circles in store 1 must equal the circles in store 1 plus an error term. And the squares in store 1 must equal the squares in store 1 plus an error term, and so on. So that's just a copy of I12 that's at the bottom. But the interesting parts of the structure matrix correspond to each of these extra nodes in the hierarchy. So let's start with store 1. Store 1 is basically going to be circle in store 1 plus square in store 1 plus triangle in store 1. And that corresponds to these 3 ones up top here. Then store 2 is circle in store 2 plus square in store 2 plus triangle in store 2, which corresponds to these 3 ones in the second row. Store 3 is the third row, store 4 is the fourth row. And now we can do Shoprite. So Shoprite Flatland is basically store 1 plus store 2. So we add all the ones from store 1 and all the ones from store 2, and we get this constraint, right? So when we add up all of these squares and circles at the bottom, we're going to compare it to the forecast that Shoprite Flatland gave for their top line. And the same thing is true for Checkers Flatland, right? And finally, the GM's number right at the top is just a whole row of ones, because you know, you're just adding up everything. And then, and then you've got the circle and the square and the triangle. And the circle is basically the circle from store 1 plus you skip, and the circle from store 2 plus skip the circle from store 3. And that's basically the idea of how you can construct a structure matrix like this that represents this hierarchy. And now that I've constructed the structure matrix, if I've got my forecasts, I can apply you know, this projection to basically project my forecasts into the space of the column space of the structure matrix, and thereby, you know, get a consistent hierarchy out that is as close as possible to all of my forecasts that I've produced. And that's what hierarchical forecasting is all about. That's pretty much the whole story. And you know, you can read more about this in Heinemann's book, but and there's a bunch of papers ranging from 2012 to 2021 on this as well. I can try and provide you with links afterwards. I didn't put them in the slides. But I want to talk about some extensions to this idea now quickly. Basically, that can take, you know, this general idea that I can take any set of forecasts and I can sort of come up with a structure matrix. And as soon as I've got a structure matrix, I can basically solve this. But there's some sort of little things to think about when you're in the real world. The first of these is, remember I said that the budget that sort of your Shoprite Flatland would have would be a lot closer. It would be a lot narrower in error than, for example, one of the store product combinations would be. Because when I'm trying to predict a store product combination, all I have to go on is the data in history, and I'm trying to trend it. Whereas when I'm looking at Shoprite Flatland's budget, I know that everybody in Shoprite Flatland is chasing that. And so there's a strong causal factor involved there. So I'm going to have a lower error. and of course, you can measure that historically, and your actual forecast itself will report an error at every time step. So in order to model errors, it's probably not a good idea that I treat every unit of error the same way, right? In what I've discussed before. And so essentially, the change that we're making here is that each forecast comes with a standard deviation or an estimate of standard deviation. We're assuming symmetric errors. We're assuming normally distributed symmetric errors for the moment. But each forecast comes with an estimate of what is its error, okay? And effectively, how do you now adapt the method that we have to deal with this sort of idea that the errors aren't all created equal? Not all forecasts have the same degree of certainty. I don't just want to hammer, error equally across all of them, because then I'm actually going to have a less likely outcome. So what I actually would like to do is maximize the likelihood of my final forecast against all of the available data, right? And so it turns out that, if you think a bit more about this, if I change this 10 to a 15, that's about the same amount of error as if I change this 25 to a 26, right? Because this error has this one has a standard deviation of 1. So I've moved one whole standard deviation away. My likelihood of doing that, you can integrate under the normal curve is like 66.67%, or don't quote me on that. It might be not that, but the point is that you have to integrate sort of what's your probability of being outside, and the tails outside of one standard deviation against this piece of information. That's how you would work out the likelihood. So, moving this by 5 and moving this by 1 is kind of equivalent, right? Moving this by 10 is equivalent to that. So moving the 20 to a 10 is incurring the same amount of error as moving the 25 to a 26. Okay, and so you can see that a good solution is going to try and put more of the error into this 20, because that's where I'm the most uncertain, and it's going to trade these off against each other. So again, kind of the intuition here is try to make the error equal at each node, and you can prove this rigorously using Lagrange multipliers. I'll leave that as an exercise to the interested viewer. But effectively, if I try to set, if I try to basically move by the same amount relative to the standard deviation, then I'm going to move by 2c here. I'm going to move by 10c here. I'm going to move by 3c here. Oh, okay, I changed the numbers, I think, to make it easier. Just ignore the fact that the numbers are different here. These are the real errors. There was an error in the errors. So I'm going to move this one by 2c, this one by 10c, this one by 3c, and this one by 5c, where c is some constant. And effectively, my total amount of error available is, as before, just 10, because I'm 10 out when I add these 3 up to get to this one. So I've got 10 units to play with. If I add 2c, 10c, 3c, and 5c, I get conveniently 20c. I wonder how that worked out so nicely. And then c must be a half. And so I can work out what my epsilons are. And that's basically now your error minimizing answer. So the 10 became a 9, the 20 became a 15, the 25 became a 23.5, and the 45 became a 47.5. And so that basically gives an idea of how you might deal with confidence in the forecast. And in general, it corresponds to weighted least squares. I'm just introducing a diagonal, in this case, covariance matrix sigma. And so I've written here a kind of a covariance matrix sigma, which is basically representing the diagonal variances, right? And those are the squares of these standard deviations. And so if you compute this, it's the same projection logic applies, just with a bit of extra geometry. And you can now take an arbitrary problem and solve it in the space of sort of having a confidence associated with all your errors. And now you really have turned a forecast where you're basically telling me, I think it's 20, but plus or minus 2. I think it's 10, but plus or minus 2, 20, but plus or minus 10. And we're using all that information together to basically come up with a new green forecast that is the most likely given all that information. And that's, I think, also, that's where hierarchical forecasting really starts to shine now, because I'm leveraging my error information. And yes, you can compute a new covariance matrix as well. Just the formula is very long, but you can look it up. So there's a whole bunch of other things to think about. I mentioned quite a few times that the units are in rands for like the ShopRite Flatland. They don't measure it in number of nail clippers that they sold. They measure it in total rand value of everything that they've sold. So they don't measure the number of circles, the number of squares. So how do you convert? How do you do rands instead of units? Does this framework allow you to do that? And I don't know whether I should leave this as an open question or whether I should answer it. Maybe I'll answer it if someone asks it. So that's a question. Does this framework support rands? Spoiler alert, it does. But how would you do that? The next one is temporal hierarchies. So how do you combine sort of because I mentioned a couple of times that I don't want to just have sort of my stores and my products adding up, but I also want to look at like weeks, months, days, and add them up, right? And that one I think I can answer. I've been looking at a single time point, right? You can imagine that I replicate this thing for t equals 2. And then I can also consider like a third dimension coming out the page where I add up t equals 1 and t equals 2 to get like 1 plus 2. And so now I can make aggregates in the time dimension as well. And it's absolutely acceptable to do that as long as you model the errors correctly when you take the sums. Then you can basically mix different timescales using the same approach. The third one is constrained forecasts. So I'm selling a certain number of circles. I don't know what it means if after I project into the hyperplane, it tells me that product 1 needs to have -5 circles. That doesn't make a lot of sense to me. And it would have happened, for example, if over here, for instance, this 20 had been a 3, right? Or something like that. Then we would have been subtracting 5 from 3 and would have ended up negative. So there's a couple of ways you can solve this. One is to add constraints to your solver, the brute force approach. The other is to ask, if I'm near 0 to begin with, is my error really symmetric? It's probably not. So the reason things go negative is because we're assuming a Gaussian error. And one trick you can employ is to take logs. When you take logs of stuff, then or to exponentiate stuff, then when you can force positivity effectively. So that is a trick that is one trick you can employ. Another trick you can employ is you can leverage constraints to basically mimic the asymmetric forecast, but that's a bit more tricky to set up. And then the third one is you can actually model your asymmetric error, like for example, a binomial distribution instead of a Gaussian one. It becomes computationally costly, but it certainly is definitely, theoretically possible to do this. And that's actually also talks to that last one, which is errors aren't normal or even symmetric. How do you deal with that? So I mean, I've given some inclination towards how you solve these things or how you deal with these issues, or just to be aware of them at the very least. But if you're interested, you're welcome to ask me more questions. The last thing I want to discuss is kind of this idea of a product of hierarchies. So, when we looked at this hierarchy here, it was already kind of a product hierarchy on the bottom and a store hierarchy on the top. But it was like a single product hierarchy and a single store hierarchy. It's actually also possible to have a product hierarchy at every level. So I could, for example, have said, what is the total number of circles sold at ShopRite? That's not a row in this matrix, right? You can see that. There's no row in this matrix to talk about just the circles at ShopRite, Flatland. And that's what you would get if you producted the two hierarchies together in the form of a Cartesian product. So I've got the product hierarchy, I've got the store hierarchy, and I just take the Cartesian product, every pair of them, and every relation between every pair. And in the most general case, I'll have a product hierarchy, a store hierarchy. I might even have two store hierarchies, for example, the ShopRite Checkers dimension, but also the Gauteng, Western Cape, Eastern Cape dimension, for example. And I'll have a temporal hierarchy, which is days, weeks, months. And these are all independent hierarchies that exist as metadata. And I can take the product of all of those hierarchies to create a monster hierarchy, which is basically this big product hierarchy, this big sort of hierarchical structure, or you'll end up with a massive structure matrix. If you think about it though, what is the size of that structure matrix? If I have 1,000 products and 1,000 stores, and maybe I'm looking at 100 different time points, and for each of those 100 time points, I'm looking at 10 different aggregation levels, maybe just 3, day, week, month, right? Aggregation levels, day, week, month, year, 4. So maybe I'm looking at 400 temporal nodes. And now when you take a Cartesian product, you multiply, right? So the number of nodes will be the number of nodes in my product hierarchy times the number of nodes in my store hierarchy times the number of nodes in my other store hierarchy times the number of nodes in my temporal. And the answer to that sum is a lot. Don't know if I'm allowed to swear, so I'm just going to say a lot. A ton. So you end up with a lot of nodes in your new sort of product hierarchy, right? And where product now is the product of hierarchies. And that means your structure matrix gets very big, like huge, billions of rows potentially. And if you have 1 billion rows in your structure matrix, you're probably not going to have a very good time inverting that structure matrix or solving linear equations with that structure matrix. It won't even fit in memory. So what can you do? And so I ran out of time making my slides, but I wrote in a very confusing paragraph that you can factor the structure matrix by essentially cutting it at various levels. So I might say, I'm going to cut the structure matrix at the region level. So I'm going to get the whole of Gauteng, the whole of Western Cape as one thing, right? And when you cut it, you basically remove everything underneath and you keep only the hierarchy above. And that's much smaller, right? And you can do this in product space by cutting in the different dimensions. And you can solve the equation, the reduced equation that comes out when you chop all the leaf nodes off, right? And that reduced equation is feasible to solve. And then you can go, you can take the solution of the reduced equation and you can basically now propagate it down to each of its sort of subtrees. And each subtree now can be solved, assuming that the solution to that equation was the right answer. And then if you really want to get clever, you can now iterate. Now you've got the solution to each subtree, you now propagate back up and back down and back up. And you can do this sort of iteration. And I have not been able to prove that this converges, but that is where we currently are in trying to sort of understand this. In practice, it seems to work fairly well, but very interested in understanding the convergence of this and what else people do when they have these massive matrices like this, but with special structure, and you're trying to solve a problem like this one, the matrix with special structure, interested in potentially unpacking that with anyone who's interested in collaborating. And that is it. I think I don't know if I'm on time or not. It's hard to tell.
I think you're doing perfectly well. I wouldn't stress about it.
Awesome.
Thanks, Dario. Are there any questions from the audience? If you have, you can either raise your hand or type it in the Q&A. I actually have a question, very broad question, actually, Dario, not specific. I found it interesting when you went through some of the methods, you started actually commenting on some of them just not being feasible in an industry environment for various reasons. And I just wanted to get your sense, like how often are the methodologies that are actually created in an academic environment actually useful in the context that you work?
I guess the difference is that, in the academic environment, the priority is the method. The method takes center stage. Whereas in industry, the problem has to take center stage. And the problem will, there will be a problem. All these approaches that I'm talking about are academic approaches. They exist and they have been developed by academics. But my feeling is, that the right answer is not necessarily the tool that you have in your hand. You have to kind of really wrangle with the problem and get to the bottom of it. And, you need to use common sense, like say, well, if I've got 100 data points, is a neural network really the right solution? And so it very much depends on the problem. But that's what makes it exciting, because, you kind of out there in the Wild West, you've got a couple of bullets in your gun and a knife, and you might have to make something out of bamboo. But I don't know if that analogy quite holds up. But effectively, you have to always treat the problem as a first-class citizen, and I think that's the biggest learning I've had.
That's awesome. I also just wanted to ask, so in terms of there are some methodologies, though, some techniques that are very fancy, they're amazing. You can imagine the amount of research articles that are published on them. But what do you think is often the biggest stumbling block to implementing a very sophisticated methodology in machine learning or data engineering, whatever it might be? The moment you step into that problem-solving environment in industry, what do you think is a big stumbling block?
So I think it's always data. So a lot of the very good techniques require clean data, or, you spend a lot of your time cleaning that data in order to use them. And I'm not saying you can't. I think in our shelf scanning solution, for example, we're using pretty much everything is state of the art there, but we can because of two things. Firstly, Google has been nice enough to basically implement all of these new algorithms on cell phones for us. So that's awesome. And that's also a big hassle sometimes, is like when the only solution that exists is like a piece of code that accompanied a paper that is not maintained and potentially unreliable. That can be a big no-no for industrial application. But it's nice when a big brother has taken care of that for you. But I think the other one is just the cleanness of the data. So you spend, I think, like 90% of the time making sure that the assumptions that underlie that model are met by the data you actually have, or that you may have to wrangle with that data to get it to that point.
Yeah. And in terms of the kind of software that your company tends to use, is there commercialized software that you tend to focus on? Do you prefer open access? Like, what is your preference? Because I know you mentioned two specific structures. Profit, I think it is one of them that definitely focus on open source. But do you often implement open source? Because obviously,
so I think we do implement a lot of open source, and I think it's when you want to understand how something works, it's very dangerous when it's a black box. So it's nice to know at least there should be a paper or something explaining how it works, so that we know that this thing is applicable to the problem that we're solving. It's very difficult. I kind of have this rule. It's maybe not the best rule for moving fast, of like, if I couldn't have implemented it myself, I probably shouldn't use it. And that means that a lot of the sort of closed source tools are not so good. But then there are really great tools out there that are more about sort of the workflow. Like there's a thing called weights and biases that we're using quite extensively. It like helps you track your experiments. We're using it again in our shelf capture side, and it works really well. The team is giving me a lot of positive feedback. And that's not an open source thing, but it's just
Yeah.
nice, you know.
I think, yeah, there are benefits on either side. I think especially when it comes to data security, there's a lot of good commercial stuff out there, but it can be expensive. So that's why I thought I'd just ask what it is that you guys end up using a lot of the time. So there's a question here from Sanele about getting access to the presentation, the recording. The recording will be accessible, but it depends on the speaker whether he's willing to share his slides with everyone. All right. Are there any other questions from the audience? If not, then Dario, I just want to thank you again. Just very much for your time and very much for your insights. I really enjoyed it myself. Would you be willing for us to actually put your presentation online? I think that would be very useful to many of the people that couldn't make it.
Yeah,
So,
that's fine, Sharif. I think I just noticed when I went through it now that I left a customer name in one slide, so I'm just going to have to remove that and then I'll share it.
Thank you so much. All right, everyone, thank you very much. Just as a brief comment, our last webinar will be at the end of November, and there we will have Langton Rogers and Gerry Style from Actuarial and Analytics Solutions at Deloitte giving us a presentation. So thank you, everyone. Have a good afternoon.
The University of Johannesburg, the future reimagined.